let's talk. Well, I'll talk. You listen. About static equilibrium. We all have our special challenges in this world. One of mine is remembering whether the word equilibrium has one or two L's. But I happen to have the physics book open next to me, and it's got that word in it. So I cheated and looked. It's only one L. So what is static equilibrium? You actually know about static equilibrium problems. We've been considering problems that you could classify as static equilibrium problems since as early as chapter 5, when we started talking about forces. Because we know when something's not moving, that's what static means, that the forces must be balanced. But now we're going to have a new, this is in chapter 12 by the way, a new addition to what we know about this, because if something is not moving, and what we're going to add to here, our sense of not moving. Back in chapter 5, when we were thinking about forces, all objects were just reduced to like a point mass. So we didn't have any concept of rotation or the possibility for rotation, at least not in our mathematical models. If an object is not moving, which means, in other words, the velocity is 0 and the angular velocity is 0. If an object is not moving, then of course it must be true that the sum of all forces is equal to 0 and the sum of all torques equal to 0. And remember that to figure out the direction of a torque, you go from R to F in less than 180 degrees, whichever way you have to do that using that right-hand rule. And the most important thing is just to remember which is which in terms of opposite. Every once in a while they ask a question on the AP test about the direction of the vector. Is it out of the page or into the page? And then you have to do the right-hand rule and make sure you go from R to F, not from F to R. Anywho, so that must be true. And that is the extent of the notes. Boom! That's it. Okay, I guess I better do a couple examples for you. So to show you about this. Actually, maybe I'll just add one little thing to the notes here. And the net torque is 0. Of course, if something's not rotating, it's a little bit harder to recognize where the axis of rotation is because it's not rotating. Sometimes there's like a, well, if it was rotating, it would be rotating around this axis. Sometimes it's a little more obvious than other times. But in fact, it's true. If something's not rotating, then the net torque must be 0 about any axis. You get to choose. So if you can choose whatever axis you want, you're going to choose the one that's going to make the problem the easiest to deal with, of course. So I'll show you what I mean here in this example. Here's a classic example. Haven't designed the practicum for this yet, but it might be, if you were live in the classroom, your lab practicum would be this problem here. So this is a lab stand, and at the top there's a scale, like a spring scale or a force sensor, and here there is some kind of like beam coming across here. I've used meter sticks for that in the past. And there's a string. Let me make this look a little more substantial. You're going to see a free response question just like this too. And let's say this is some angle theta. And the reading on the scale is, let's say, 2 newtons, and theta is equal to 30 degrees. And let's find mass of the stick, meter stick, or whatever rod it is there. Okay, so how do we do that, and how does it have to do with this stuff? So the first thing we need to do is make a force I'm going to call it a force/torque diagram. What's the difference? When you're making a diagram and you care about torque, then it's important that you preserve the shape of the object and you actually pin the forces at the right places. So let me make that diagram. So instead of just making a dot, I'm going to make a little copy of the object. So what forces do we have? Well, there's force of gravity. Where do you put that? Well, when you play pin the tail on the donkey, or pin the force on the force/torque diagram, a really fun game to play with kids, birthday parties and stuff. You put that force on the center of mass. So this is mg here. Now there's a tension force here. That's at 30 degrees. I'm just going to copy that into my diagram here. And what else is there? It can't just be those two things. Those two could be balanced torque-wise, because this is trying to get it to rotate this way, and this one's trying to get it to rotate this way. So those could balance for torques, but there's no possible way that those two forces could balance, because this torque has a xy component, xy components. So this, the up part could balance that, but this, no, it's not happening, right? The horizontal part of this torque could not possibly be balanced by that. So where are the other forces? Well, there's this rod's attached to this hinge here, and that hinge, it's where exactly, what's going on here with the hinge force? Well, I don't know exactly. I don't really feel super confident like drawing the direction of it, but probably it's pushing back on the rod this way, and it might also be kind of like supporting the rod a little bit. So what I'm going to do is I'm just going to make those components of it. I'm not going to presume that I know what direction it's going, so I'm just going to make those two components. All right. So I'm going to show you a failed method for doing this. So this is a fail. I'm just warning you. Forces must be balanced. Great. So we'll hand this off to our Chapter 5 physics student and see what they can do. So in the left-right direction, in the x direction, we have this component and, this fx, which would have to be equal to the cosine component of t, right? And in the y direction, ups would have to equal downs, so it would have fy plus the other up would be t sine 30, and that would be equal to mg. All right, and then it's off to the races, right? Wrong. because there's an fx, an fy, and a t. That is 3 variables, and I have 2 equations. And that ain't going to work. If you got 3 unknowns, you're going to need 3 equations, not 2. So this is 3 variables, only 2 equations. Boo. No good. So that does not work. It's true. I mean, these equations are true. It's just not enough information. So instead, we're going to try the torque approach, which is what you're going to try first, because you got this great preview. Torques must be balanced. Now, what do you think we should pick about for the axis? There's 2 ways you could think about this. You could think about, well, if this was going to rotate, doesn't this seem like more axis-like than other things, like if the string broke or something like that? It doesn't seem like it's going to suddenly start rotating here, I guess if it came unhinged. So I don't know if you would agree with that or not, but I think intuitively this is the most axis-like location. And if you don't like that, here's the practical reason why we're going to choose this, is because if we choose this to be the axis, any forces that are acting at that axis are going to get knocked out because torque is equal to force times radius. And what's the radius for forces that are actually acting at the axis? It is 0. So, oh, I forgot to tell you how long this thing is. Well, I'm not going to tell you. I'll just call it L, right, is the length of that rod. Maybe it's a meter stick. Maybe the L's 1, but it turns out we don't need to know. I'll show you here. So torques must be balanced, and then I'm going to choose, and I'm going to say right here that the axis is going to be the hinge. You could choose any axis, but this is the one that's going to work because it's going to knock out those 2 forces that I don't know. Okay, so let's see if we can write that net torque equation. There are 2 torques once I pick this axis. There's this one, and they're trying to get it to rotate in opposite directions. So that means if we're only looking at magnitudes, the magnitude of the torque caused by this must equal the magnitude of the torque caused by this. So the torque from tension must equal, and notice I did not put a vector sign on this, so this is indicating the magnitude of that, must equal the torque caused by the gravitational force. What do those look like? The torque caused by tension is force times radius times the sine of the angle between them. So that's T times the radius, that's the length, the full length of this thing, right? That's from axis to point where the force is acting, times the sine of the angle between them. That must equal the torque caused by gravity, which is mg times the radius. This is only acting at half the length, times the sine of the angle between them. That's 90 degrees, so that's just 1. And that is our equation. Notice that the L's cancel out, so I get, what am I solving for? M here, so M is going to be equal to the sine of 30 is 1/2, so that 1/2 and this 1/2 cancels, so it's just going to be T over G in this case. Oh, and I guess we knew what the tension was. It's that. So, what's that? About 0.49 or something? No. Hold on. 0.2-ish. 2 divided by 9.8. Right. That's how you do that. That's an example. I will warn you as you go to, I think the first set of problems you're going to do in the book is 3 through 11 odd from chapter 12. And I think the first 3 of them, 3, 5, and 7, hold on, I've got a book right here. I'll tell you for sure. I think that you don't need to use torque in those. It's just kind of like a review of static equilibrium with forces. Nope, just kidding. It's these first 2. Those numbers 3 and 5, you do not need to use torque. So just keep that in mind, please. And then when you get to 7, then you start to need to use torque. There'll be a video with the solutions for all of them. So there you go. Enjoy.